The next type of sampling we're going to be looking at is ray sampling. And the way ray sampling works is that from a certain pixel, rays are fired in random directions into the scene and return with information about the color or the reflections that are encountered. And the more rays you fire, the less noise you're going to have, but the longer your render times are going to be. So to demonstrate this, I've created this blurry reflection on this sphere here. And I've done a test render, so if I open my render window and I zoom in, you can see there's quite a lot of noise on the blurry reflections. So the way we fix this is we find the material and we increase the number of reflection rays. So just under where it says blurry reflection, what I'm going to do is I'm going to multiply the number of rays by 4. So that gives us 256 rays. And I'll just pause the video while I do a test render. And this is the completed render, and I'm going to zoom in and compare it with the previous render, and you can see that the new render is much cleaner. It's pretty smooth. And let's compare the render times. The initial render took 18 seconds and this one took 33 seconds. So obviously it has taken longer, but we fired quite a few more rays, so that's not surprising. So the main thing to take away from this is that in order to control blurry reflections, you need to increase the number of reflection rays. You shouldn't be thinking about anti-aliasing or the shading rate. However, there is one caveat to this. The settings aren't quite fully decoupled, and I'm going to show you this right now. So I've defined a render region around part of the reflective sphere. And now I'm going to return to the scene and just change a few settings. I'm going to go to my global anti-aliasing and I'm going to make sure it's set very low. And make sure my base shader is set to 1. And now I'm going to return to the material with a blurry reflection, and I'm going to set the reflection rays down to a very low value of 16. So with these very low quality settings, I'm expecting a noisy render, which I'm sure I'll get. I'm just going to pause the video while I do a test. And here is the completed render. And if I zoom in, you can see that it is indeed very noisy. But this time, instead of increasing the number of reflection rays, I'm going to change the shading rate and the anti-aliasing settings. So I'm going to go to my main render item and I'm going to set 256 samples per pixel. And now I'm going to go to my base shader because the shader in the material itself is disabled at the moment. And I'm going to reduce the shading rate to 0. And now I'm going to pause the video while I do another test render. And now the render's finished, let's zoom in and compare it with the previous render. Well, you can see it is indeed much cleaner. But remember, I didn't increase the number of reflection rays this time. I left them at 16, which is a very low value. What I did do was to increase the global AA and reduce the shading rate to 0. If I compare that with the render where I actually increase the number of reflection rays, the results are very similar, almost identical. It would appear that the latest render is just very slightly noisier, but that's all. So what exactly is going on here? What's happening here is that the reflection ray value is not fully decoupled from the shading rate. So what exactly does this mean? Well, this means that when you have subpixels as defined by your shading rate, then each one of those subpixels is going to fire a reflection ray. It doesn't really matter in this particular case what is set in your material in terms of reflection rays. So in this case, we've got 256 samples per pixel, and that means that every single one of those subpixels is going to be firing one reflection ray. So the result is that we're getting 256 reflection rays per pixel, even though we'd only set the value in the material itself at 16. But this does come with quite a big catch. If we compare the render times, this frame, where only a small render region was defined, rendered in 49 seconds, whereas this frame rendered the entire frame in just 33 seconds with cleaner results, so it was considerably faster. And that's because using a coarse shading rate with a high number of reflection rays is a much more efficient way of cleaning up blurry reflections than trying to refine the shading rate, because when you're refining the shading rate, you're also going to increase the anti-aliasing quality, and that is going to take a longer time to render. So when you're trying to clean up blurry reflections, the first thing to do is to increase the number of reflection rays and leave the shading rate alone unless you need to reduce it for other reasons. Now, of course, there are some materials when you'll need to reduce the shading rate as well as increase the number of reflection rays. but in those cases, reduce the shading rate according to your other problems that you are encountering and specifically target the blurry reflections with the right number of reflection rays, and that way you'll get the most optimized materials. With any form of ray-based sampling, be it reflection rays or global illumination rays, anything that's going to fire rays into the scene, there's another setting that you need to be aware of, and that is the ray threshold. And I'll explain why here. I've modified this scene by enclosing the spheres into a box, and I've applied a material with some blurry reflection to the entire scene. And I've already applied 256 reflection rays to this material and done a test render. If I zoom in, you can see that it's quite noisy, particularly in the area underneath the spheres. Now, if you remember, on this material, 256 reflection rays was enough to give us a clean result, but in this case, it isn't, and I'll explain why. In this scene, we have more complex interactions between the surfaces and the reflections. There's recursive reflections, that is, reflections within reflections. And Modo uses an algorithm called importance to get rid of rays, to cull rays whenever they encounter a surface. So the more times a ray bounces, the more ray culling is going to take place. And essentially, the more bounces you have, the more recursive reflections you have, or the more GI bounces you have, the fewer rays are going to survive. This is done in order to optimize render times. Now, the default value is very aggressive and will cull a large number of rays. In simple scenes, this isn't a problem, but once your scenes get more complex, you need to adjust this by decreasing the ray threshold. So what I tend to do is to decrease it by a factor of 10. So I do this by adding an extra 0 behind the decimal point, and then I'm going to test to see if that's sufficient. And if I return to the render window, I've already defined a render region, so I'm going to make sure that render region is being used, and I'll just pause the video while this renders. And with the render complete, if I zoom in on the area where the render region was and compare it with the previous render, you can see that it's noticeably cleaner. So just remember, when you have these complex scenes, it's important to adjust the ray threshold. At this point, in order to get a clean render, it's a question of balancing the right ray threshold value with the right number of reflection rays on the material. You want to be aware that obviously using the ray threshold is a global value, whereas adjusting materials is a more localized value. So ultimately that's more efficient. So only decrease the ray threshold just as much as you need to get the best possible results. Another attribute that is controlled by firing rays is the quality of area lights. So I've set up this scene with a little bit of GI, but the environment's very dark, and there's an area light lighting this sphere. I've done a test render, and if I zoom in, you can see there's a couple of problems with it. First of all, there's a little bit of noise here on the edge of the shadow, but the other thing is the shape of the highlight. You can see it's round, but the light is actually square. And the reason for this circular highlight is this attribute here that's found in the light's properties called simple shading. What this does is to use a simplified model to calculate the specular highlight, the diffuse shading, and the shadow of the area light. This obviously renders much faster with less noise, but it lacks realism. So if we untick simple shading, and I just unpause preview, you can see there's quite a few changes. First of all, the shape and the intensity of the highlight changes. And also we're going to find there's probably going to be a bit more noise in the render. So I'm just going to pause the video while I do a test render. And here is the completed render. I'm going to zoom in and I'm going to compare it with the previous render. You can see that the shape of this shadow changes quite dramatically, and there's quite a lot more noise here. The same applies to the highlight. The shape has changed and there's more noise and less intensity. So using simple shading means that we get faster calculations at the cost of realism. However, when we turn simple shading off, we're going to need to increase the samples in the area light in order to get better quality of shading on the edge of this shadow, on the border of this cast shadow, and in this highlight. So I'm going to return to the scene and increase the number of samples in the area light to 256, and I'll just pause the video while I do another test render. And here is the render, so let's zoom in and compare it with the previous render. And you can see that there is indeed quite a lot less noise, simply by increasing the samples on the area light, we've reduced the noise here on the edge of this shadow, in the highlight, and on the border of this car's shadow. Now, had we left simple shading on, we probably still would have needed to increase the number of samples in the light because this car shadow was still quite noisy.